Hello and welcome. In this video, we're going to be taking a look at how to define a couple linear shapes in 3 dimensions. Now, when you think linear, you might think a line. That's one of the couple things we're going to be taking a look at. Although we know how to kind of define a line in 2 dimensions, it's not going to be exactly the same sort of process in 3 dimensions, although there's some similarities there. But we'll be taking a look at planes as well, and a plane is a linear shape, at least in 3 dimensions. Let's start off with that and figure out how we would come up with the equation of a plane. Now, there's a couple pieces of information that we're going to need in order to define a unique plane. The first piece of information that we'll need is a point on this plane. We'll call that P naught, and that could be at any point on the plane. In here you can see I've just put that point on this green plane, and we're kind of looking at that from first octant view. Now, a second thing that we're going to need is a normal vector. This normal vector is a vector that is perpendicular to the plane. And with those two pieces of information, we can define a unique plane. Now, it's a little bit tough to see this normal vector in 3 dimensions, but you can imagine you have a piece of paper and the normal vector is just sticking out. And that's coming from any point on the plane, but it is perpendicular or orthogonal to this entire plane. I'll draw this normal vector from that point P naught, and you can see that at any line that we draw along the plane, this normal vector is going to be orthogonal to the line. All right, well now it's time to define the plane. And this will be an equation for every point on this plane. So why don't we define an arbitrary point P with the coordinates x, y, z? Now here is that point, and that just represents an arbitrary point on the plane, and we want to have an equation that dictates what x, y, and z values we would need to choose so that the point will always be on this plane. Well, we have to be a little bit creative at this point in time. What we'll do is use a little bit of what we learned on vectors, and we'll define a position vector for the point P naught in standard position. And so I'll have a vector pointing from the origin out to P naught, and why don't we call that R naught? And that would be a vector, a position vector for that particular point that we are given on the plane. And then we'll do a similar process with the point P, and we'll define a position vector for the point P in standard position, and we'll call that R. Those two position vectors. And with those two position vectors, we can actually define another third vector that is very handily on the plane. From P naught to P, that particular vector can be actually calculated as the difference between R and R naught. Specifically, that vector there is R minus R naught. And you can confirm that with vector addition. That vector in purple, R minus R naught, when it is added to the vector R naught here in blue, then the two vectors sum to R. So it does make sense in terms of an equation. And here's the handy part. That little vector, R minus R naught, since it is on the plane, by the definition of perpendicular here with this normal vector, the dot product of n and R minus R naught must equal 0. And that gives us this beautiful equation. Any point on the plane P, x, y, z has a position vector R, and that position vector must obey this equation, n dot R minus R naught equals 0. Now this is kind of a bizarre looking equation, but this in fact is an equation that dictates every single point on that plane. So we call it the equation of a plane in R3 in vector form. Now, of course, we're not necessarily used to having objects and surfaces like this defined in a vector form. Luckily, we can find out how to create a simple scalar form of this by expanding that dot product out. If our normal vector, let's say, has the components a, b, and c, and then we have r being the position vector x, y, z of an arbitrary point on the plane, and r naught being the position vector x naught, y naught, z naught, then by simple vector addition, r minus r naught is the vector x minus x naught, comma, y minus y naught, comma, z minus z naught. The dot product of those two vectors must equal 0. That's pretty easy to expand out. Component-wise multiplication from the scalar product or dot product, and then we can expand and collect some terms. This gives us ax plus by plus cz, where x, y, and z are the components of an arbitrary point on the plane, minus ax naught plus by naught plus cz naught, all of that being subtracted in parentheses, and that x naught, y naught, z naught is a specific point on the plane that we already know. Now, since x naught, y naught, and z naught are just simple constants, they're just scalars, then we could collect all this together and maybe just call that value d. And when we move it to the right-hand side of the equation, then we get the equation of a plane in scalar form. ax plus by plus cz equals d. And sure enough, you can see that that is a linear equation. Now here, as you can see, we've got a linear equation for a plane. But what if you just think back to 2 dimensions? Ax plus by equals a constant, say d. That would actually be the graph of a line in 2 dimensions. So that linear equation now is actually graphing a plane when we have 3 variables. So that means something is going to be a little different when we try to graph a line here in a little bit and try to come up with an equation for a line. All right, well now we know how to take the couple pieces of information we need and come up with the equation of a plane. Let's try visualizing this over in Maple. Now here in Maple, I've got the plots and vector calculus packages loaded up. And first of all, let's suppose we've got a point 362. Well, I'm going to define the position vector for that point, r0. And that's going to be useful, as you'll see in a moment. We've also got, let's say, a normal vector, -2, 3, 4. With those 2 pieces of information, we should have a unique plane. Let's start off by visualizing the normal vector. Now with the normal vector, I don't want to plot that vector in standard position. Luckily, with the arrow command, I can plot any vector I like with any initial point I want. That's where I'm going to need the position vector r0. That is going to be the initial point of the vector I want to plot, and I want to plot the vector n. So you have to kind of make sure those 2 pieces of information are inputted in the correct order. The rest of these parameters are just to make it look pretty, and so that the vector will show in red in my final plot. So let's do those first things. Next, we're going to have to plot the plane so that we can visualize this. Now let's take a look at the vector form first. N dot r minus r0 equals 0. Now the vector r I've just put in here manually as x, y, z. Now I've got a semicolon, so I can do a second command, and I'm just going to solve that in vector form for z, so I get the scalar form of the equation. Now you can see there is the dot product. That'll give us a scalar form right away because Maple will perform that dot product for us. And if you solve that for z, then z is equal to x over 2 plus 5 minus 3/4 y. That is how we will plot the plane. Here we're going to use the plot 3D command, and with that command we need to plot an equation of the form z equals a function. So here is that function for the plane, and we'll plot from x equal -1 to 6 and y from -1 to 10. And then we'll display both those together, and it might not look quite right initially, but that's okay. That's just not proper scaling. You can see that the scales for x, y, and z are all going to be slightly off from one another. Up here at the top, we're going to constrain that scaling. Now you can see perfectly perpendicular red arrow to that plane. And our point P is at the initial point of that red arrow. So you get a better sense of what we're really doing here. Using a point and a normal vector, we can define a unique plane. Probably the most important thing to remember with planes is that we need 2 pieces of information. We need a normal vector and we need a point on the plane. With those 2 pieces of information, then we can go ahead and we can form the equation of a plane. Now there is maybe another option here as well. If we don't have a normal vector, then there is maybe one other way that we could come up with the equation of a plane. If we know 2 vectors that lie in the plane, let's say we have maybe a vector A, and maybe we have a second vector B, with those 2 vectors, a normal vector could simply be calculated with A cross B or B cross A. Those vectors will be pointing in opposite directions, but they are both going to be perpendicular to the plane. Keep in mind that there's not necessarily just one single unique normal vector for a plane. Any vector that is perpendicular to the plane would be a normal vector. Now with that in mind, let's try a quick example of finding the equation of a plane that passes through 3 points. Now, if we're given 3 points on a plane that will define a unique plane. There isn't going to be more than one plane that passes through those 3 points. Similarly, in 2 dimensions, 2 points is enough to give a unique line. That doesn't necessarily mean that the equation is unique. Of course, you could always have a scalar multiple of that equation, and that would define the same plane. Here we've got the points P, Q, and R. Now, right away, what we'll have to use is this technique of coming up with 2 vectors that lie in the plane. And we could simply just look at the difference between 2 points to create 2 different vectors. So long as the vectors are not parallel to one another, then we can take their cross product and get a perpendicular vector. Let's maybe take a look at the vector PQ. From P to Q, that would be 3 units in the positive x direction, 1 unit in the positive y direction, and 3 units in the negative z direction. And why don't we use PR as our second vector? Now, specifically chosen PQ and PR so that both vectors have the same initial point P, although that's not necessarily imperative. We would just need to have 2 vectors in the plane. Now, let's decide which normal vector we want to look for. We could go with PQ cross PR or PR cross PQ. Doesn't really matter. I'm going to define this positive normal vector to be PQ cross PR. And we'll use our determinant method with I, J, and K, our elementary unit vectors in the first row, PQ in the second row, and PR in the third row. And maybe this is a good time for you just to pause the video and double check and make sure you know how to do this cross product and calculate that normal vector. You could also use Maple or another computer algebra system for this problem. Here, I've calculated that normal vector as -8, -9, and -11. Now that we've got the normal vector, we just need a point on the plane. And we're lucky here. We actually have 3. You could choose to use P, Q, or R. And of course, like I said, the equation may not be unique. You can choose any of these, and you may have gotten a slightly different normal vector, but they will end up being an equivalent equation. The equation for our plane in vector form is n dot r minus r naught. And so that will be the vector -8, -9, 11, dot product with x minus the point P, -1, y minus 2, and z minus 2. But feel free to use Q or R for this. And of course, that is equal to 0. Now, if you like, you can leave this in vector form, although maybe as it is right now, it doesn't quite look like it's going to be very useful for future applications. So let's choose to expand that out. We'll distribute the -8, -9, and -11 component-wise. Be careful of some of these negative signs. We have our -8, 18, and 22 as constants. Adding those together is 32, and we can move that constant to the other side to kind of get this nice standard form. Now with that, we end up with loads of negative numbers. So maybe it's just better to multiply both sides of the equation by -1, and that'll give us the equation 8x plus 9y plus 11z equals 32. Of course, any scalar multiple of that equation would be an equivalent equation for the plane. All right, why don't we take a look and see what that looks like over in Maple now so you get a better visualization. All right, so I've got my plotting tools and vector calculus, which is maybe a bit overkill, but quite handy just to be able to do a few of our vector operations. And we've got PQ, PR, both defined right here. Now I'm defining n again as PQ cross PR. We can calculate that all very easily in Maple. There's our cross product. And then we can take a look at the vector form of the equation. Now this didn't show up perfectly, but you can see that is a dot product. N dot, although it just looks like a period, n dot x plus 1, y minus 2, z minus 2. So once again, I'm just using the point P there. And then once we get that equation, we can solve that for z. That solve command will simply just isolate z so that this next line here is the equation of that plane in the form of z equals 32 over 11 minus 8 over 11x minus 9 over 11y. That's going to be important so that we can graph this using the plot 3D command. Now, I've got a few different plotting commands here. P1 is going to be a tool that plots vectors, that's arrow. It's going to have the initial point -1, 2, 2, and we're going to be plotting the vector PQ. Our second plot is going to be, again, the initial point P and the vector PR. So that'll be able to visualize both of the vectors that we're using to come up with the equation of this plane. Here in P3, though, we have a plot 3D command. It has to be of the form z equals something, which is why I've taken that equation of the plane and solved it for z. And we'll just graph that from x from -3 to 3 and y from -3 to 3. With those three different plots, we can display them all simultaneously, and we can see our vectors PQ and PR lying on the plane. So sure enough, we can double check that we've done all of the math correctly here using a powerful tool like Maple. All right, well, now that we've got the basics of coming up with the equation for a plane, there's a couple other common things we might want to know about planes. For instance, how do two planes intersect one another? Now, it is quite possible that two planes never intersect. And just like with lines, that would happen when the two planes are parallel. You can try to see this in this little picture here. We've got our red plane, let's say it is the plane A, and our blue plane would be the plane B. Now, their normal vectors could be pointing either in the same direction or in exactly the opposite direction, in which case their normal vectors are parallel. Now, we've seen parallel vectors before, and we know that one of those normal vectors is simply a scalar multiple of the other. We could say that our normal vector of the plane A is equal to k times the normal vector of B, where k can be any real number, positive or negative, but not 0. It's also possible that when two planes intersect, that they are perfectly perpendicular to each other. And as you would expect, that only happens when their normal vectors are perpendicular. You can see that here in this picture as well. In this picture, we've got our red plane A and our blue plane B. And sure enough, if they intersect at a right angle here, which we can indicate, then their normal vectors are also going to be at a right angle. And because those normal vectors are perpendicular, it must obey this dot product property that the dot product of those normal vectors is equal to 0. Okay, well, what if the normal vectors are not perpendicular and they're not parallel? Then we may wish to determine the angle between these two planes. It may help to visualize these two planes from sort of a side view. If we're looking at this plane A from a side point of view, basically like we are a point on the plane, then, well, it would just look like a line from this particular angle. And here's the normal vector forming a right angle with that plane. Then we've got our second plane in blue, and again, from a side view, this is going to just look like a line, although it is actually a plane when we take a look at the three-dimensional view of this. And we have the normal vector forming a right angle. Now you can see I've drawn two angles here. We might look for the angle theta in green between our planes A and B, or we might be looking for this purple angle phi between the planes A and B. There are actually two possible angles that we could be interested in. If the planes are not perpendicular, then we may be looking for the acute angle, or we may be looking for the obtuse angle. All right, well, time for a little bit of geometry here. We can form a four-sided object using our planes in red and blue, as well as the normal vectors. We may just have to extend a couple of those vectors until it forms this four-sided object. Okay, well, I have made this four-sided polygon, or a quadrilateral, using the angle theta as one of its included angles, and I've moved the normal vectors for A and B to the top corner so they have the same initial point. And that would be exactly at the corner opposite our angle theta. Now, since the angles in a quadrilateral add up to 360 degrees, or 2 pi radians, and we have two right angles, that means that the opposite angles, theta, and the one over here at the top, must add to 180 degrees, or pi radians. Well, we already know that theta and phi add up to 180 degrees, so this angle at the top must be phi. We also have another property of intersecting lines from geometry, that the opposite sides of that intersection have the same angle. So the angle between our two normal vectors is also phi. We do know how to find that angle using our dot product. Cosine of phi is equal to the dot product of our two normal vectors na dot nb, and then we divide by the norm of each of those vectors. That will allow us to figure out one of the two possible angles between our planes, simply just taking a look at the angle between their normal vectors. However, if that maybe is not the angle that we're looking for, if we're specifically looking for either the acute or obtuse angles, then it's pretty easy to find theta. Theta will simply be the difference, pi, or 180 degrees, minus phi. And that'll give us the two angles between our intersecting planes. Now, we will be revisiting planes again in the future, but let's take a look at our other linear object of importance in R3, which would be the equation of a line. Now, a line is a little bit harder to illustrate on this page. That green line in first doctrine view could be pointed slightly towards us or slightly away from us. Now, once again, we can define a unique line using similar information. We'll need two pieces of information in order to define this unique line. The first thing is maybe just a point on the line again. We can call that P naught, and that'll be at some coordinate x naught, y naught, z naught. So let's put that point here on our graph. Second of all, we're going to need a direction for this line. That would just be maybe in the form of a vector. Not the normal vector in this case, but let's just say we have a vector, we'll call it v, with the components a, b, and c. That's telling us which direction this line is pointed. With those two pieces of information, we should have a unique line. Now, to come up with the equation of this line, let's let P, again, just be an arbitrary point anywhere on the line. P could equal P naught, but let's just let P be anywhere on that green line. Just like with our plane, we're going to take a look at a couple position vectors, R naught and R. And remember that the vector from the point P naught to the point P is simply just the difference, R minus R naught. As we see in this case, that vector in purple, r minus r naught, is parallel to the vector v. That means we can start forming an equation. Since v is parallel to r minus r naught, that means that r minus r naught is a scalar multiple of v. Now, this is going to make it look a little bit strange, but we're going to let t be that scalar multiple. R minus r naught equals t times v. Well, with this, we can then rearrange the equation a little easier than with the plane. R, being the position vector of any arbitrary point on the line, seems like the best thing to solve for here. This would give us the equation R equals r naught plus t times v, where t is any real number. If t is equal to 0, that'll give us the position vector of the point P naught. And if t is any non-zero value, that'll give us a point either further along or further behind the line from the point P naught. And this is the vector form of that line in R3. But, as it turns out, this would also apply to n-dimensional space. Essentially, just give it a point and a direction vector. T allows us to travel anywhere in that direction, either forward or backwards, and that works even in R2 or higher dimensional space. This t in this case is called a parameter. Given a value for that parameter, then we can find a point anywhere on that line. Now, once again, if you don't like this vector form of that line, then we can try to see how we turn this into sort of a scalar form, and that might make a little more sense depending on your intuition. In three-dimensional space, r is going to be the position vector of an arbitrary point, x, y, z, and r naught is the point that we are given, x naught, y naught, z naught. Our vector v has the components a, b, and c in three-dimensional space. And this is a vector equation. We can go ahead and use scalar multiplication as well as component-wise addition on the right-hand side. That gives us x naught plus at, y naught plus bt, and z naught plus ct. Now, we have two vectors that are equal to one another. And the only way that two vectors are equal is when each of their components are equal. So the only way that we can really turn this into a scalar equation is by actually coming up with a system of equations. We have x equal to x naught plus at, y equal to y naught plus bt, and z equal to z naught plus ct, where t again is any real number. This is the scalar form, but it's a parametric form. We don't have an implicit equation of x and y. We have three separate equations given in terms of the parameter. Now, of course, if this is in 2 dimensions and we only have x and y, and we scrap that z equation completely, then you have two equations, and it is quite possible to solve for t in either the x equation or y equation, substitute it into the other one, and then you have a closed form equation, an implicit equation involving just x and y, no parameter anymore, and you can see that that right away gives you a linear equation in x and y in 2 dimensions, and that is a line. However, we can still solve for t in all three equations and set them all equal to each other. And what we get there is what we call the symmetric form of a line in R3. Solving for t 3 times and setting all the results equal to each other gives us this symmetric form. And we may not use that one nearly as often, but it is a way to come up with the equation of a line without using that parameter. Now, it's fairly simple to derive the equation of a line given those two pieces of information. It's just scalar multiplication and vector addition. So you can try out a couple examples on your own, but instead, I want to maybe take a look at how lines and planes interact with a couple examples. In this first example, let's suppose we have a line, and here is scalar parametric form. You can see we have an initial point, 4, 3, negative 5, and you can come up with a vector in the direction of that line by looking at the coefficients of the parameter. Negative 1, 2, and 1 would be a vector in the direction of that line. Where is that line going to intersect this plane? 3x minus 2y plus 4z equal negative 8. You can see this is in 3-dimensional space. It's got those 3 different variables. It's not exactly necessarily intuitive the first time you see this. We have the equation of a line using a parameter, and we have the equation of a plane, which is simply just an implicit closed form equation with just x, y, and z. There's a couple steps that we actually have to do. Just like when we're trying to intersect lines, we can substitute the equation of one line into another and solve in R2. Well, that's kind of what we're doing here. We're going to take the equation of the line and substitute that into the plane. Hopefully that part of things will still be somewhat intuitive, even if we are in 3 dimensions and we have a parameter. So we'll take our x equation, y equation, and z equations for the line and plug those into the plane. Now, this comes up with an equation involving only one variable, but it's actually the parameter that we can solve for now. By expanding and collecting terms, this gives us negative 14 minus 3t equal to negative 8, which gives negative 3t equal to 6, and that gives us a value for t. T equals negative 2, but that is actually the value of our parameter. That doesn't give us a point in 3-dimensional space. This is only 1/2 the problem. Now that we've got that parameter, if you remember, like I said before, given any value of the parameter, we can come up with a point on the line. We've already got the equations given to us for x, y, and z. That will be our point. We simply just need to plug in t equal to negative 2. And that gives us the point 6, negative 1, negative 7. Well, we've seen now how a line can intersect a plane, and that would intersect at a single point. Although it's possible that a line may never intersect a plane if they are actually parallel to one another, in which case you wouldn't be able to solve for t whatsoever. Now let's take a look at how planes intersect. With planes, they could be parallel, and they may not intersect, although it's possible that those two equations are actually equivalent, in which case they are both defining the same plane. It'd be kind of like parallel planes that intersect at every single point. However, if that's not the case, then when two planes do intersect, they don't intersect at a single point, they actually intersect along a line. Is it possible to find the equation of that line given just the information about those two planes? Let's suppose we're given the two planes, 2x plus y minus z equals 6, and another plane, 3x plus 2y minus z equals 8. Right away, from the coefficients of this blue plane, 2, 1, and negative 1 for x, y, and z respectively, we can come up with a normal vector for that plane. Why do we call that NA? 2, 1, negative 1. And similarly, with plane B in red, we know a normal vector for that plane would be 3, 2, and negative 1. What can we possibly use that information for? Well, here's a little sketch of those two planes. And we're looking for that purple line. That's the line of intersection. That line exists on the plane A, and therefore that purple line must be orthogonal to NA. That purple line also exists on this red plane B, and so it must be orthogonal to NB. In fact, that purple line is orthogonal to both NA and NB. We know how to find a vector that is perpendicular to both of those normal vectors. It's simply that we have to calculate the cross product. So if we wish to find a vector, let's say v, in the direction of that purple line of intersection, we could go ahead and use NA cross NB or NB cross NA. Once again, you should try this cross product on your own. I'm going to use NA cross NB and see what we get when we look for that vector v. And I will end up getting 1, -1, and 1 with my particular choice of cross product. Okay, well, we have one of the two pieces of information that we need in order to define the equation of a line. By going back to the equation of our line, we need this second piece of information, r0. T is simply a parameter, and we already know v. Now, the good news about trying to find that point is that there are infinitely many to choose from. This is a line. It goes on infinitely. However, how do you find just a single point on that line? Well, again, some good news here is that we see that none of the components of v are 0. That means that the domain of x, y, and z, since our parameter t is any real number, x, y, and z can also be any real number. We have a little bit of freedom here. We can go ahead and we could just let, I don't know, z equal 0, for instance. And then we can find a specific point on that line where z equals 0. It would be the point where this purple line crosses the xy plane, and maybe that will help us a little bit. Let's say we're looking for a point P0, and we'll have z equal to 0. Well, that will allow us to plug 0 into both of the equations of these planes, and we'll have two variables and two equations to work with. That will allow us to solve for x and y. Of course, there are many different methods to choose from for how you solve this system of equations. Personally, I do like using elimination a little bit. If you know some linear algebra, you can even turn this into a matrix problem. I'll let you go ahead and try to solve this on your own and see if you can come up with the values for x and y. Using whichever method you prefer, you should find that x is equal to 4, y is equal to -2, and of course, we've chosen z to equal 0. You can even go ahead and plug those values into the original equations of the two planes, and you should see that you end up with 6 and 8 for the values on the left-hand side. This point satisfies both of those equations. Then, of course, we can go ahead and finally state the equation of the line, and maybe we'll just keep this in vector form. We'll have the position vector for that point, 4, -2, 0, plus a scalar multiple, our parameter t, times our direction vector 1, -1, and 1. If you'd like to expand that out and write that into scalar parametric form, then by all means you'll have 3 equations for x, y, and z. All right, well, I hope that sums up those linear objects in three-dimensional space. There's more than one. We've got a plane, which is an implicit equation, ax plus by plus cz equals d. That's a scalar form, and it looks like a linear equation, simple enough. And we also have a line which you need that parameter. We're going to have to introduce a parameter, maybe t, and that will allow us to have a straight line in three-dimensional space or even in higher dimensions. Both these are going to be quite useful when we're taking a look at calculus in multivariable functions. So stay tuned. Thanks for watching, and I'll see you in the next video.